this session, and I will be posting it in Google Classroom. So in the case that you would like to go back and view the lesson, it will be available for everyone to have access to that. So what we want to do this week is that we want to compare internal and external forces in the Caribbean. We want to describe earthquakes and volcanoes, and we want to distinguish among the three main processes that occur in rivers. So this is what we want to accomplish content-wise this week. So what is our lesson for today about? It is about internal and external forces. Internal meaning inside of the earth, and external meaning on the surface of the earth. So we're going to be looking at those two things and how they work hand in hand, and how the internal forces affect the external forces of the earth. So before we begin on talking about internal and external forces, we want to talk about the earth. So the surface of the earth is made up of a thin layer of soil with solid rock underneath. And most of the external forces, are like earthquakes and volcanic eruptions, occur on the surface of the earth, be it on land where we can visibly see it, or underwater where it's still a part of the crust but not that visible to us. So my question to you guys is, what are the three main and distinctive layers of the earth? Anybody would like to respond? Don't be shy. You can put it in the chat or you can unmute. What are the layers of the earth? You have the crust, you have the core, the third one?
Mantle.
And the mantle. Very good. So we have the crust, which is the outmost layer, the mantle, which is the middle layer, and then you have the core, which is the center. So we're going to be looking at these three distinct layers in detail. The first one is the crust. Now, as I mentioned, the crust is the outmost layer, so where we are, what we can see, it's the surface of the earth, and it's a little bit in depth. It's not as thick, so if you take a look at the diagram, the little white line, that is the depth of the crust. It's very, very thin compared to the other layers of the earth. The crust is the least dense layer of all. Who can tell me what dense means? Nobody knows what dense means? Less hot. Less hot is okay. We can put it. That's one way to put it. Dense means that, okay, very good. Close, like when I pack up something. So if I'm going to go on a vacation and I only have one suitcase, I'm gonna put as much things as I can in that suitcase. And the more things that I cram in there, then that's the more dense I make my suitcase. So the same thing applies with the earth. The crust is the least dense layer, meaning that I could go in my backyard and I could dig a hole and I could do that. Maybe I might get tired, yes, but it won't be as difficult as me wanting to go through the mantle or through the core. It's the least dense layer, so it's the least compact, meaning that the crust does move and can move. And for example, if we have an earthquake, that's why it's easily the surface of the earth opens, because it's the least dense. It's not that compact, it's not that tightly stick together, right? The crust is composed of solid rock made from mostly silicone and oxygen, and that is the reason why it is dense layer. It's the least dense layer. Moving on to the mantle. The mantle is the middle layer. It is the thickest layer. Its density increases with the depth. So the deeper that we go through the mantle, that means the more dense it gets because of the pressure. The deeper that we go into the earth, everything that we are passing is on top of that, and that pressure makes it more dense, makes everything that we go deeper into more compact. It's composed of softened rock and contains iron and magnesium. The core is the inner layer, so it's at the center of the earth. It's made of the heaviest material and it is the most dense layer of all. It is composed of iron and nickel. So if we go back, the crust is made of silicone and oxygen, and if we weigh silicone and oxygen, those are very, very light materials. The mantle is made of iron and magnesium, so we're getting a little bit heavier. And the core is made of iron and nickel, which are very heavy metals. All right, so as we go through the layers of the earth and we move from the crust to the mantle to the core, then everything gets more denser and there is more pressure being applied. So I saw this answer in the chat. I'm not going to be asking what are the two regions the core is divided into: the inner and outer core. All right, so the core has two parts: the outer core, which is the one in yellow, and the inner core, which is the one in white. The outer core is made of slow flowing liquid, and it is molten rock. When we say liquid, that doesn't mean that water is floating around in the core, right? It's a heavy metal melted liquid that makes up the outer core, while the inner core is a spinning solid. So it's like we have a ball right in the center of the earth made of very, very hard material, and it's just there spinning in the center of the earth, all right? So my question now is, what are the two regions that the mantle is divided into? We have the core divided into the outer and inner, but now what is the mantle divided into? How do we call the two regions that the mantle is divided into? Upper and lower. Very good, Tristan. So we have the upper mantle and we have the lower mantle. So the upper mantle is the one in red and the lower mantle is the portion in orange. The upper mantle is made of mostly ultramafic silicates, and the lower mantle is more rigid and made of magnesium and silicon oxides. So I am just giving you the composition of these different layers, but we don't have to memorize them or learn them. It's just for your knowledge so that you understand how later on when we go on to the different landforms, how these things play a part in it. Now, what are the two regions the crust is divided into? The crust is where we are, right? So what are the two layers of the crust? Or the two regions that the crust is divided into? Water and land. Okay. The crust has two components basically. We have land where we are, and then we have the water component to it. So when we're referring to it in terms of geography, we refer to them as the oceanic crust and the continental crust. Continental crust, basically the land, and oceanic crust, basically the water component. The oceanic crust is more dense than the continental crust. The oceanic crust is made of basalt, and the continental crust is made of granite. So these that I have here, except for lithosphere and asthenosphere, we're not going to be looking into those, but the other 6 layers are the ones that you need to be able to recognize. Oceanic, continental crust, upper and lower mantle, and inner and outer core. 6 layers. All right? Anybody has any questions so far? Anybody has any questions? Okay, good. So what I'm going to do now is that I'm going to be playing a video that talks about the formation of the continents. So let's see.
Flying past the Earth at this time, we see a vast blue ocean beneath a red-tinted sky, punctuated by volcanoes and small land masses. And unlikely as it seems, life may have gained a foothold already. That life in the oceans that gave birth to it may actually be vaporized many times by cataclysmic bombardments, which have slowed but not yet stopped. Earth has begun to take on its final form, a crust, a skin so thin it would be less than a sheet of paper were the Earth the size of a basketball. And under that, a molten semi-solid mantle that boils in extreme slow motion. And finally, 2 cores, a liquid iron core pulsing out a magnetic field that helps shield us from a deadly cosmic wind from our sun. And a solid nickel and iron inner core. By now, the remarkable process of plate tectonics has kicked into gear. Though how and when it started exactly, we do not know. For what follows next, you might want to strap yourself in. It's going to be a bumpy ride. Here's how it might have happened. At first, Crotons and one continent called had the planet all to themselves. Then, around a 500 million years later, Antarctica took shape. About another 500 million years passed before Atlantica formed. The continents roamed separately until, about 1.8 billion years ago, Antarctica collided with what is now Eastern Antarctica to form Nina. Then Nina, Atlantica, and collided 1 billion years ago, forming the supercontinent Rodinia. After about 300 million years, the 3 landmasses separated and came back together in a new configuration, Pangaea. Pangaea came apart too. When Pangaea split, and Atlantica split up too. If you're confused, join the club. Even the Earth seems confused. All of this movement made for a host of unlikely neighbors way back when. North America's eastern seaboard once rubbed shoulders with Chile. California and Australia were neighbors, if not connected. And Brazil was either connected to Nigeria or very close.
Okay, so what was shown in the video? Now, the video is just extra information so that you guys could see that the crust didn't always look how it looked right now. So we have several different continents right now, but at some point all of it was just one big chunk of land on Earth that moved. Billions of years ago, the movement of the Earth was more vivid. You could clearly see the movement of the Earth. Right now, we are moving, and if you would search on the internet and you would Google information, you would know that the continents are moving. Each year, they move a few centimeters. It's not something that you could see immediately. If I take a picture um, from space of the earth, you could see that, okay, Africa is somewhere else. No, it's moving, but it's moving at a very slow pace. Now, what is the reason behind that? So if you want to explore more about the layers of the earth, I do have this link here, which is just an activity from an online source, and you could explore more information about the different layers of the earth. All right. So what we want to concentrate on today are the crustal plates. And there are several different crustal plates. 1 second, guys. Where is the link? What is the link? August 26, Mantle. Is this it?
Who is someone you admire, and why do you look up to this person? Nobody. I'm sorry. I don't want to call names.
Yeah, di ba? Diligent ko si Kay. Ito mo kas. Okay, sorry about that, guys. So talking about plates, plate tectonics, plate boundaries, crustal plates in general, what we're going to be doing is that we are going to concentrate on the different movements of the crust, but I will show you guys the information about all the crusts that are found on all the plate tectonics that are found in the Earth's crust. That does not mean that you have to go and memorize all of them and label the map, right? It's just for you guys to see how the crust looks like when it comes to a map of the plate tectonics. So now, what is a crustal plate? It's a rigid segment of the Earth's crust which can float across the heavier semi-molten rock below. So, simpler words, the crust, because it is less dense, it has these big chunks of rock that are floating. Now where we are, a little bit under the crust, right where the crust and the mantle meet, there are the plate tectonics that are floating on top of the molten mantle that is there. So because they are floating, that leads to movement that happens because of these plate tectonics. All of these are the divisions and the different plate tectonics that the Earth's crust is composed of. Some of them are very larger than other ones. For example, the Antarctic plate, the Eurasian plate are very large plate tectonics compared to the Caucasus plate or the Caribbean plate, which are very small in size, right? Or the Scotia plate. Belize is on the North American plate, not the Caribbean plate, right? So, talking about tectonic plate boundaries or plate margins. In the previous diagram, we looked at the different plates. We are going to be looking at the movement. So, when the Eurasian plate moves, where is it gonna move if we have all of these plate tectonics close to each other, right? There is not a space in between the Eurasian plate and the North American plate. There's not like a big hole in between them that nobody can cross. All of these plates have to be moving, but if everybody is right beside each other, then the movement can be very difficult for that to happen. So we have three different forms or three different ways how plate tectonics can move. They can be transformed, meaning that they can slide beside each other. So one is moving forward, one is moving backwards, and they are sliding. And it doesn't happen fast. It's not they're gonna go like sliding and sliding and sliding, right? It happens very slowly and slow that you cannot feel it. We're not here and then I can feel the plate tectonic underneath me moving, right? This movement is so slow it cannot be felt. We have diverging, that they are moving away from each other. So one is moving that way and the other one is moving that way, moving away. And then we have converging, where they are moving towards each other. And these plates can go back. These plates can experience the three types of movement. For example, the Indian plate could be moving away from the Arabian plate, but because it is moving away from the Arabian plate, it is moving towards the Australian plate. And because it is moving away from one towards the other, it is sliding right beside the Eurasian plate and the African plate. So that Indian plate is all three different movements in one. Right? So when we are talking about how we are going to be labeling and how we are going to be calling these divergent, these plate boundaries, we have to talk about two of them. We have to say the Indian plate and the Eurasian plate are transformed to one another. The Arabian plate and the Indian plate are diverging from one another. And the Indian plate and the Australian plate are converging to one another. So that is understood that on that border, that is where that movement is happening. Is that clear? Anybody has any questions so far? No questions? Okay, thank you for responding. Thank you. We're gonna move on. And this is what I was talking about, right? See the different movements. This is just for your knowledge. You want to go over the PowerPoint later on, then this is there for you guys to see, right? Want to explore more about tectonic plates? I do have another link. It does have the interactive. It has little video diagrams where you can see the movement that is happening. If you want to go, you can go ahead and click the link and you guys can view that. This is a little online game about plate tectonics and plate boundaries. You want to just do it for fun, it is there, the link is there, you guys can go ahead and do that. Now in this one, you need to at least have an idea where the plates are, because it does give you some questions asking what movement this certain plate has. Now, as a result, so now we're going into what we really want to know. We have these plate margins, we have these movements that are happening, transform, converging, diverging, but if that is happening underneath the crust, how does that affect what is happening on the crust, on the outer layer of the crust? So we have what we are going to talk about today: volcanoes and earthquakes. And we're going to look at how these plate boundaries and these plate movements cause these things to happen, right? So, looking at the first one, volcanoes are formed where magma is able to penetrate to the Earth's surface. So we don't have a volcano everywhere in the country, in the world, sorry. In the places where we do have volcanoes, it is because underneath, below that volcano, there is a little hole, there is a little vent that allows for magma to come out to the surface. So, when two plates are moving away from each other, there is a space that is created. And that space allows for whatever is on the mantle to come up to the Earth's crust. So I have the video of an earthquake, right? The image of an earthquake and the different layers of the earthquake. You will have to go back and review this. What I want is to show you guys a video on earthquakes. So let me play this for you.
Portals into the heart of the earth, they burn. Bottomless cauldrons fueled by an ancient wrath, bubbling and boiling thousands of miles beneath the surface, and just waiting to burst through. Volcanoes are scattered across the planet. About 1,500 active volcanoes can be found across the world, though countless others are on the ocean floor. Most volcanoes, whether on land or underwater, are located where tectonic plates meet. In fact, the Ring of Fire, a path that traces the boundaries between several tectonic plates around the Pacific Ocean, contains about 75% of the planet's volcanoes. There are several types of volcanoes, primarily classified by shape and size. Major types include stratovolcanoes, which often appear as tall, steep mountains; shield volcanoes, which are flatter and dome-shaped; calderas, which are large depressions in the ground; and mid-ocean ridges, which are underwater chains of volcanic mountains. No matter their shape or size, all volcanoes emit gas and molten rock. The journey of these emissions begins deep underground in the Earth's core. The core, which can burn as hot as the surface of the sun, transfers its heat to the surrounding rocky mantle. In doing so, the heat melts some of the rock. This molten rock, or magma, is lighter than the surrounding solid rock layer, so it rises through the mantle. The magma then escapes through vents in the Earth's crust, causing volcanic eruptions. Now above ground, this magma is referred to as lava, and it can reach temperatures of over 2,000 degrees Fahrenheit. In addition to lava, volcanoes may erupt with searing hot gas formed in the mantle. In a phenomenon called pyroclastic flow, this gas, combined with hot ash, can race down the sides of a volcano as fast as 100 miles per hour, burning everything in its path. To measure and classify eruptions, scientists developed the Volcanic Exclusivity Index, or VEI. It considers various factors, such as the volume of lava, gas, and other emissions from the volcano, along with the height of the eruption cloud above the volcano's summit. The VEI scale begins at 0. Each successive measurement increases logarithmically, meaning that each magnitude is 10 times more powerful than the one before it. The VEI scale does not have an upper limit, but the most catastrophic eruptions measured thus far are categorized as VEI 8. These eruptions occurred thousands and millions of years ago. The most destructive volcanic eruption ever witnessed occurred in Indonesia in 1815. Mount Tambora, a large stratovolcano, erupted with a VEI measurement of 7. The blast caused earthquakes, tsunamis, and pyroclastic flows that decimated the land and took tens of thousands of Indonesian lives. The eruption even destroyed the top of Mount Tambora itself, turning the 13,000-foot tall mountain into a 3,640-foot deep caldera. While volcanoes are some of the most destructive forces of nature, they have also helped make life on Earth possible. Volcanic ash provides nutrients to nearby soil, making the land fertile. And lava, when it cools, hardens into rock and creates new landforms. With heat from the heart of the Earth, volcanoes have helped terraform the planet, making it the rich, dynamic landscape we see today.
Okay, guys. I think I mute. Okay, guys. So that was a video on the volcano. Basically, they explain how a volcano erupts, and they gave you a little bit of history on the biggest eruption that there has been witnessed, and when they mean that it has been witnessed, meaning after in AD, right after the death of Christ. That's what they mean. So that's 1815. Let me move on. So now earthquakes, and we're gonna do the same thing. I just gonna give you a little background on earthquakes, and then we're gonna watch a video on earthquakes. Because what time do we finish? 10:35. So I think we have enough time. No, we don't have time. We won't be watching the video. So now earthquakes occur at fault lines. Most earthquakes occur at convergent, divergent, or transferring planes. So meaning that earthquakes can happen at the three different movements. And it's easy for an earthquake to happen if we have converging, means that they are moving together and they crash. Two land masses crash, that causes a rupture in the earth, and that causes an earthquake. If two of them are moving away from each other, then they're leaving this space in between, and if there is no magma there to erupt up, then the land automatically falls in, and that's why we have those big cracks in the earth after an earthquake. And transform, if they are moving side to side and suddenly they get trapped, meaning that they get stuck, then that when they're forcing each other to keep sliding, not because they get stuck or they get caught on something, then the plate tectonics freeze. They continue moving and they do their best to move. So if at some point they get stuck, they're gonna continue moving, and that force causes for an earthquake to happen. You guys can view the video if you would like later on when you have the time to do that, but I do want to get to, there is a video for the earthquakes.
From above.
Sorry. Again, I have another link if you want to more about plate boundaries. Now, the first assignment that I have posted in Google Classroom, 4 questions need to be responded. I did post the activities separately, so you can go ahead and complete this one and upload it, and then later on do the other one and upload it. This one says students will research any one volcanic activity or earthquake that has occurred in the Caribbean or Central America. So it has to be Caribbean or Central America within the last year. So anything from 2020 or the beginning of 2021 works. Based on the information, respond to the following questions. Number 1, briefly describe the volcanic activity or the earthquake. You're only doing one by providing the magnitude, the location, the date that it occurred, and any other little detail that whatever research site you are using provides to you. So, for example, a volcanic activity happens on a scale from 1 to 8. An earthquake also happens on a scale. If you have constant listen to the news, you have 6.7 earthquakes. The magnitude of an earthquake usually is a decimal point. The location, meaning what island or what country did it occur. If you chose a volcano eruption, where did it occur? In Haiti, in St. Vincent, where? The earthquake, the same thing. The most recent earthquakes in the Caribbean happened in Haiti. Just an example if you want to go there. The date that it occurred If the website or your information provides you with a time that it occurred, then that's fine. You can put that as well. Second question, describe the magnitude of damage that emerged as a consequence of this disaster. So if you did a volcanic eruption, what was the aftermath? What does the aftermath look like? What did the country look like after the earthquake eruption? And the same thing with an earthquake. After the earthquake incident, what happened? How did the country look like? How did the people experience that damage? So you're just explaining. And number 3, explain how the physical geography of the Caribbean or Central American country was altered as a result of this occurrence. Usually after a volcanic eruption, certain all of the agriculture around the volcano is no longer there. That is one effect. That is one way that it affected. Other volcanic activity does cause an extension in the island. For example, when the lava cools down, especially in the islands, if it cools down, it hardens and extends the island a little bit. And then the earthquake, how has the earthquake affected the physical geography? Well, there are certain areas where if there was a mountain, the mountain breaks and you have one piece being higher than the other one. You have roads that are no longer available for usage. You have faults, you have big holes and cracks in the ground. All of those are how it affected the island afterwards, or the country afterwards. And then the last one, describe the economic difficulties that arose as a result of this disaster. And that one should be pretty easy. After an earthquake or after a volcano, what is the financial difficulty that a country goes through? Do they need to be requesting medical assistance, assistance for construction, donations from other countries? Do they struggle with finding drinkable water? Do they struggle finding food? All of those things. What are the struggles? And that one is more general. You don't have to talk about it with your specific country or your specific incident. Number 4 is more general. What happens after, in the aftermath of a disaster? Even in Belize, we experience hurricane. What do we experience after a hurricane? What are the difficulties financially that we experience as a country? Right? So number 4 is more general. How are you going to be answering these? You will write number 1, the question and your answer. Please use at least the most 3 sentences to respond to each one. I don't want a big explanation or a very lengthy answer. Right? Go direct. Tell me what your answer is. I don't want a whole lot of things that you're just repeating and repeating and repeating. Go direct to your answer and just tell me what it is. If you can respond to number 1 in 1 sentence, that's fine with me. That will work perfectly. Right? The ones that will take you a little bit more to explain, number 2, number 3, number 4, you will have to say a little bit more, but the most 3 or 4 sentences will do the job. All right? Anybody has any questions with the assignment?
No, miss.
Okay, good. Now I gave you guys a link that has a list of volcanic eruptions and a list of earthquakes that happened last year. Make sure that if you're using these websites only give you the name and the location, right? And then you have to go and you have to search more information on your own, but those are a list that you could use from. And then a reminder, your flex activity.